So hi, everyone. I'm happy to be here. So this is the first time I'm actually presenting in English. So I think my English is pretty good, but I'm kind of nervous. So we'll see how it goes. This talk is titled Secrets, Race Conditions, and Statelessness. My dad, who knows nothing about tech, first thought it was about the NSA doing coups in foreign countries, but it is not. This talk is about a nasty bug related to managing secrets in Kubernetes. And due to this bug, when it happened to me, it happened twice. The first time, well, what happens is a stateless service randomly and suddenly became stateful. And I'll get into what I mean by that. And the first time I came across this bug, I just figured it's bad luck and it's never going to happen again. But then it happened again. And I realized it's an engineering problem. And so this led me to think a lot about different ways to manage secrets reliably. And I want to share those thoughts with you today. So like Lynn said, I'm an SRE based in Paris. I work for a company called Pigment. I'm not going to go into details about what we do. We're basically building an Excel on steroids in your browser. So we store and process a lot of data, and it's user data. So security is a thing. And so credentials that give access to the different databases where we store that data are very sensitive. So we take secret management very seriously. You can find me on LinkedIn, GitHub, Twitter, whatever. I don't post a lot on Twitter, but I have some cool projects on GitHub, so you might as well take a look. So let's say we have a simple stateless service on the left that contacts another service. Let's say it's PayPal, for example, to process payments. And we use an API key for authentication. So we don't store that API key in our Git repo, right? Although we all started that way. And we store this API key in an external secret storage service. Okay, so most cloud providers offer such services. They're usually called Secret Manager or something like that. You can also use HashiCorp Vault as a managed service or self-hosted. We use Vault self-hosted, by the way. And you can even store secrets in a bucket. I mean, it doesn't matter. What I'm going to talk about today still applies. And so what's so great about external vaults like this is that they're great for security and auditability. That's hard word to say. So basically, integration with the cloud provider's IAM system allows for fine-grained access control. Well, this is great because that way, like, specific services can only read specific secrets, and also keeps track of all reads and writes. So in case of a leak, when you find your credentials are online or for some reason, you can find out who read the secret and when, and that way you can start to follow the breadcrumbs to find out, okay, where is the security problem that allowed the leak to happen. And so we generally don't want our service to include a client that contacts the vault directly because that would lock us in. Okay, it's a bad abstraction, and also it's painful when you're developing locally because that means you need to have Vault instance on your laptop. Anyway, it's a pain. So we have the service read the API key from an environment variable. So we all do this, right? This is what Heroku recommends in its 12 factors. And this works really well when you're developing locally because developers can have a file with the API key in it, and that can be sourced as an environment variable when they run the service. And we, as SREs or platform engineers or whatever you want to call yourself, as owners of production and staging environments, we can provide this environment variable in any way we wish. And this freedom allows us to do it well. So how do we do it? So as you probably know, Kubernetes has a built-in mechanism for managing secrets. There's a secret object in the API, which is just an object. It's not encrypted or anything. And you can pass the contents of this object to your instance, so to a pod, as environment variables, right? By just mentioning the secret in the pod's spec. And so this works really well, and it's what a lot of people do. It's what we do. We did. Right. But the thing is, like, you need to keep that secret in sync with your secret manager, okay? Because this isn't your source of truth, right? Your source of truth is your external secret manager. So a popular solution for this is to use an operator. There's a popular one that's called external secrets that was first developed by GoDaddy. Or HashiCorp actually recently released their own operator that's currently in beta that has a very similar design. And so how do these operators work? So we, as software engineers, we create an external secret object in the Kubernetes API. So it's a custom resource. And that external secret object to the top right contains a reference to our secret, right? So it just says, this is the secret name, and this is the version I want to get. And we include that external secret object in our services manifests, usually, right? So in our Helm chart or whatever. And so step one is the operator reads this external secret object. Step two, the operator connects to our external secret manager and reads the value of the secret. Step three, it writes that secret to the Kubernetes secret object in the Kubernetes API. And step four, we have kubelet, so the Kubernetes agent, that reads that secret and uses its contents as environment variables when it's running our services container. So with this approach, what happens when we rotate a secret? So let's say I get an email from PayPal saying my API key expires tomorrow. So I go to PayPal, I generate a new key, and I add it to my secret manager. So now I have a V2, right, of my secret. And both versions coexist, right, and both are readable. Okay, so they have different values and they have different IDs. So what I do is I update my external secret manifest. So top right, now it references V2, right, of my secret. And so the operator sees that change, right, reads version 2 from my vault, and then writes that new value to the Kubernetes secret, so it updates the secret in place. And then kubelet will use that new value for any new pods, any new instances of my service. So if I just perform a rolling update of my service, right, at the same time, because maybe I have this clever mechanism where the ID change of the secret suddenly changes the pod spec with like a checksum or something. We all do this. It's like in the Helm docs, so everybody does it. So that triggers a rolling update automatically, and my new instances use the new API key. So mission accomplished, right? Well, no, because this can go subtly wrong twice because of a race condition. And so, to go over what a race condition is really quick, because most of you probably know, is a race condition is a situation where the outcome of a process depends on the ordering of multiple concurrent steps, okay? More formally, it's when one actor changes some data while other actors read that data, and the order in which those operations happen is non-deterministic. In other words, and this is the way I prefer to say it, if two programs use the same data at the same time, things get weird. So the simplest example of a race condition is you have two threads, T1 and T2, and they both want to increment a shared variable that we're just going to call n. And maybe that variable starts with a value of 10. So the first thread reads the value 10, right, computes 10 plus 1, and writes the result 11 to the variable. Then the second thread reads the value of the variable, so 11, computes 12, and then writes 12 to the variable. And this is fine if it happens the right order. But if it happens this way, you can have both threads reading 10, both of them computing 11, and then both of them writing 11. And suddenly, you were supposed to have incremented that variable twice, but you didn't. Okay, so this is the basic example of a race condition. And race conditions happen all the time in real life, right? If you and your roommate bought twice the amount of milk you needed because you didn't synchronize, that's a race condition, okay? So it happens all the time. And race conditions are a very painful bug because they emerge in systems that have many moving parts, so they're hard to diagnose. And their trigger is usually semi-random because it's about timing, and that can make them very difficult to reproduce. So can you spot the race condition in this workflow? What if I told you that step 4 can happen before step 3? And let's see how that can happen. So when our deployment pipeline updates our external secret and our Kubernetes deployment to trigger that rolling update, both the external secret operator and the Kubernetes deployment controller start working at the same time, asynchronously, right? They don't synchronize. And most of the time, the operator updates the Kubernetes secret faster than our service can start. And so the secret is up to date when our service starts, and so it reads the new API key. But sometimes something can go wrong, right? We're SREs. Things going wrong is why we have a job. And so maybe the external secret operator is down at that moment, or maybe your secret manager is unavailable. So the operator will retry reading the secret, but during that time, there's a window where your Kubernetes secret is not up to date, right? It's an invalid cache of the contents of your vault, right? And I've been told that cache invalidation is hard, and it is. And so during that time, our service continues its rolling update. So a new instance of our service starts, but with the old credentials. And then whatever was blocking the operator from updating our secret, maybe it goes away. Maybe our vault is back up. Maybe the operator isn't buggy anymore. And so it updates the Kubernetes secret. And now our rolling update continues and new instances of our service start, but with the new credentials this time. And once the rolling update is complete, you have different instances of your service using different credentials. And so your deployment pipeline says that everything went well, right? The rolling update is complete, the secret is synchronized, everything is okay, everything is green. And everything goes well until the next day when your first API key expires. And then suddenly you have certain instances that work and others that don't. And so you suddenly have multiple instances with different behavior. And the whole point of a stateless service is that multiple instances of the same service have the exact same behavior. So I started to ask myself, is this service really stateless? And if there is state, where is it? So before talking about where the state is, just here's how to fix production. Just trigger another rolling update, right? That'll fix it, okay? It's very easy to fix, and this is what we did, because first part is fixing production. And so restarting this instances just reads the new API key, and it's very easy. So where is that state? So the first question I asked myself is, are environment variables state? Which sounds like a weird question. And the answer is no, thankfully. So for environment variables to be state, they would need to be mutable. But the thing is, once a process is started, you can't change its environment variables. So that can't be it, right? Environment variables are not data, they're configuration. So the state must be upstream somewhere. And so let's take a look at where we store our credentials. There are two places we store it, in the secret manager and in the Kubernetes secret. In the secret manager, the contents are immutable and they're versioned, right? You can't get more stateless than that, right? If I refer to a specific secret by its ID, I am gonna get the same value every time, okay? So that's not it. Because for a race condition to happen, I need write operations, so I need to mutate something, and I can't mutate something if it's immutable. Immutability is your friend. That is the real lesson here. However, the Kubernetes secret is not versioned, and it's actually actively mutated by our operator. And so if you think about it, the state that plagues our service is the value of the Kubernetes secret at the time our instances start, right? So this tuple of information, like the Kubernetes secret plus a date, is state, right? If your date changes, this value of your secret changes. And so this wouldn't be an issue for an immutable secret, because then the date would not be a factor in its value. But here it is. And so that's where the state is. And so the real question is, how do we manage it? And so I'm going to talk about 3 ways, but there are many more. Find me after this talk if you want to discuss them. The first one is the easiest, and it's just to fix forward by just restarting our service automatically. Basically, doing what I did to fix production automatically, like every time. The second one is to take a step back and try to find an approach where there isn't state, right? To make our service truly stateless again, right? Before we introduce this operator. The third one is to simply embrace the state and design this a stateful system in a way that makes it reliable. Okay, so let's dive into each. So the first one is, as old as time itself. Basically, every time the secret, not the external secret or the vault secret, but like the Kubernetes secret object that is referenced in your pod spec, when that changes, trigger a rolling restart, right? And that guarantees that our services are always start after the last write operation on the Kubernetes secret. And so that way, their environment variables are always up to date. So in other words, the latest read operation always happens after the latest write operation. So we have some sort of guarantee in the ordering. And so if the race condition bug ever happens, this approach automatically fixes it. So it doesn't prevent the bug, but it does reduce its impact. And this is definitely the easiest way out of our predicament. It's quick and easy to set up, and it doesn't require changing anything that we already have, right? We're just adding another thing. And it fits well into the Kubernetes paradigm, right? Where many controllers are each doing a thing concurrently. Here we just add like a rebooting controller, basically. And so you can do this with open source tools. There's one called Reloader that does exactly this. And if you're using HashiCorp's operator that's in beta, it can actually do this for you as well. However, this option doesn't address the core problem, I think. It doesn't address mutability, right? The fact that we have state that can change over time. In fact, we now have two actors responsible for restarting our service, right? We have a deployment pipeline and maybe Reloader, right? Or this new controller. And so who knows what other race conditions we just created without realizing. So I think we can do better. So let's look at option B, which is eliminating the states, but that requires that we take a step back. So let's imagine that each instance of our service has a reference to the secret that it needs to use, and it fetches it directly from the secret manager, right? So the top instance references v1 and the bottom instance references v2. They both fetch it, right? And maybe this reference is directly in the pod spec or something, but they both fetch it from the vault and they both get deterministic values, right? So that's really good. It's reliable. Determinism is our friend. So this design is nice. There's no race condition here because nothing is mutable, right? The contents of the vault are mutable. Our configuration is immutable. So what's wrong with this? Well, the problem is we broke that abstraction we had, right? Now our services have a direct dependency on our vault, which is not what we want. So how can we abstract away our vault from the point of view of our service without introducing mutable state in the middle? And the trick is to add a shim to our service. So a shim is just something you just stick between two things. So the shim fetches the secret and then provides it to the service as an environment variable. And so solutions like this already exist. If you run on GCP, and use Secret Manager or store your secrets in a bucket, you may have used Burgless for this, which is managed by Google Cloud. And if you use HashiCorp Vault, there's this tool developed by Bonsai Cloud that's called Bank Vaults that does also this. However, if you use AWS or Azure or Scaleway, because I'm French, try to use Scaleway a lot, we believe. This design is likely new to you. So here's how it works. So when the container starts, the shim starts first, right? It runs before the service, and it will be the one to run the service later. So the shim is PID1, right? And it reads the container's environment variables and finds any environment variables where the value is a reference to a secret. It fetches that secret from our secret manager, and then it replaces the value, the environment variable's value with the secret's value. But it can't do that, right? Because you can't change environment variable for running process. So it doesn't do that for itself. That's when it starts your service with these new environment variable values, right? So your service doesn't even know there's a shim, doesn't even know there's a secret manager. It just reads in its environment variable and finds an API key. So this is very good abstraction, actually. And if we change secret manager, you kind of just need to adapt your shim. You don't need to change anything on your services side. So this is a good abstraction. If you want to use this shim, you can add it to your container image directly. So if you have a container image somewhere that's called shim image with the shim executable binary in it, you can just copy that into your container image and then update your container's startup command so that the shim runs first, and then you pass the shim like the command it needs to run to start your service. And this works really well. You can also set the command at like the Kubernetes level if you want, but I like setting it in the Docker file directly. And so this is fine for images that you build yourself, but not really for third-party images. You don't want to maintain Docker files of every image you run just to use this shim in there. So Kubernetes has an elegant solution to this, where you don't need to build custom images to use the shim at all. And so the solution is mutating webhooks. So you probably have heard of this before. But basically, you can configure Kubernetes so that whenever a pod is created, Kubernetes sends the pod spec to the webhook, and the webhook modifies the pod spec to add that shim in there. And the webhook can also have additional logic, like optionally adding the shim only if it's necessary, et cetera, et cetera. This is how Istio injects the Envoy proxy into all its pods. So if you work with Kubernetes often, you may be wondering, like, how do I change a container's startup command? And it's surprisingly easy. So on the left, you have the barebone pod. On the right, you have the pod mutated by the webhook. I'm not going to go into details, but notice that it isn't a huge change. And so Burgless and Bank Vaults, which I mentioned previously, they have webhooks that do this. And this setup with a mutating webhook that adds this shim, it's complicated, right? So it's complex. It's Kubernetes magic. So is it worth it? And as usual, it's all about trade-offs. So let's start with the bad stuff. The first thing we lose compared to using the external secrets operator is a form of caching, right? I mentioned this, like the race condition we have is a stale cache, but now we don't have a cache at all. What this means is that if your vault is down, your pods are not going to start, right? So you kind of need to think about how reliable your vault needs to be so that you can start pods when you need to, because you need to start pods when you're deploying, you need to start pods when you're auto-scaling, things like that, pretty much all the time. And so you need to start thinking about what is your SLA for being able to deploy, what is your SLA for being able to auto-scale, and adapt your vault's SLA accordingly, right? And also, like I said, it's Kubernetes black magic, right? I mean, I created a deployment that had no mention of a shim whatsoever, and my pod suddenly has a shim, right? I mean, it's weird. And if you're not really used to it, it can be a really great way to shoot yourself in the foot. But assuming that none of this is a deal breaker, what's so great about this? Well, the first thing is we don't have a race condition, which is cool. The second thing is that everything is immutable, so it's reliable. Yay, determinism. The third one is that and I didn't mention this earlier, but with the external secret operator, you kind of have like this single service that's reading all of your secrets from your vault. So you kind of lose the advantage of having a vault in the first place, which is, fine-grained access control and auditability, right? You kind of have this deputy that stands between your vault and yourself, and you need to trust that deputy entirely. And if that deputy has a bug, that can be bad. Here, no pod can read every secret, right? Every pod has its own identity with its own access. Another bonus, if you kind of squint, right, is that this fails fast, right? So the bad part is you need a highly available vault. The good part is if your vault is unavailable, your pods are not going to start in a weird state. They're just not going to start at all. So time for a shameless plug. As I said before, you already have options for GCP and HashiCorp vaults. But if you use AWS Secrets Manager or Azure Key Vault, introducing Whisper, which is this shim, right? It's fairly simple. You can read the code. It's not a big software project. I'm working on support for Scaleway's Secret Manager, which just became GA. And I haven't had the time to write the webhook yet, but this works. And I know of 2 companies that use it in production, one of them in Kubernetes without the webhook. They just built the shim into their container images. And another one that actually uses it in a serverless container runtime on Azure. Like they don't even use Kubernetes at all. And this actually works well for them. And so I use it for personal projects. I'm not saying you should use it, but please feel free to try. And the thing is, I've had no issues with this because the design is so simple that there's never a headache, right? It just works. But that simple design also means it has limitations, right? So that's why, well, because of these limitations, we actually don't use Whisper at Pigment. And so I talked about both option A and option B. So option A, restarting everything. Option B, eliminating the state. But thing is, like you can pick one that works for you, but it doesn't work for us because we have a lot of credentials and we rotate those credentials very often for security reasons. And thing is, both of these options require that you restart your service when your credentials change. Except restarting a service can actually, A, take a long time. If you have a lot of instances, and B, can actually cost money because if your cluster needs to scale up to allow this restart and then scale down again, well, for a short period of time, your infrastructure is more expensive. So it's not necessarily what we want. And at Pigment, we have a lot of databases, each with their own credentials, and all of these credentials rotate automatically. They're very dynamic thanks to Vault. And so options A and B don't work for us. And so that leads to option C, embracing the state. So we can't keep our services stateless, right? But now we know, okay, so our services are all stateful because of secrets. So we need our services to fetch credentials from the secret manager on a regular basis without needing to restart. We can't do this with environment variables because they're immutable, but we still need a good abstraction, right? We don't want our services to just pull Vault on a regular interval. That's not going to work because we don't want this sort of lock-in, right? We don't want our developers to be thinking about Vault. We just want them to be thinking about environment variables or something as similar. But environment variables can't change, so we change the contract. The contract is no longer read your environment variables. The contract is, here's a file, right? This file is going to contain valid credentials eventually. It is your responsibility to read this file on a regular basis or to watch it for changes or whatever you want, but this file is going to contain your credentials eventually. And so if you think about it, Vault is a database, right? It stores secrets. All write operations happen on the Vault server, and we want each instance of our service, each pod, to have a partial read-only replica of that database. That's what we're talking about, right? And database replication is a solved problem. We know how to do this, right? And we know the issues with this. We know the risk with this. And so now we can we can design our system accordingly, right? To mitigate the risks that come with database replication. And here's how we do it. So we're going to combine elements of A and B, and I'm going to go quickly because I'm running out of time. So each instance of our service gets an agent, right? And so it's kind of like the shim from option B, except the agent isn't just going to run at the start. It's long running, right? It's going to run for the entire lifetime of the pod. And it's going to keep that file updated on a regular basis. And so the agent is the one contacting Vault and keeping that file up to date, and our service is just reading that file. So they have a shared volume to share that data. And so whenever the secrets are updated or are rotated or whatever, the agent updates the file. And the agent has in-depth knowledge of how Vault works. Our service does not. Our service just reads a JSON file. And it's kind of like the agent is acting like a dedicated external secrets operator for our pod. But the big difference is every pod gets a dedicated agent, so we still have this notion of identity. Right? Each pod is unique, and our agent is therefore unique, and therefore Vault can act accordingly by keeping track of this pod read this secret at this time, et cetera, et cetera. If you're using dynamic secrets in Vault, this is amazing because now every time your agent reads a secret, it's different, right? It's unique to that pod. So every single pod gets different credentials, and that way, if credentials ever leak, we know exactly which pod used them. And if we need to rotate a secret, it's as simple as deleting the pod that uses them. Because then, since no agent is there to renew the lease on the secret in Vault, Vault is just going to expire that secret anyway, right? So this is it's really cool because we don't have to restart our entire service if we ever get leaked, if we ever get hacked. But we can, and if we need to renew our services, we can do it without actually needing to restart anything, because once the files are updated, our services are supposed to use these new creds. So this design is definitely the most complex of the three I've talked about, but it's great because you can rotate often, you get precise access control and audit logs, and you don't have that race condition because you're actually acknowledging that you have state, right? The problem with the external secrets operator approach is that you have state, but you didn't know about it, and so it bit you, right? We didn't invent this design, by the way, with the agent. If you Google Vault Agent Injector, you'll find everything you need. It works really well. And so I've just showed 3 different setups. There are more. But so what's the lesson here to conclude? And I think there are a few. The first one is don't half-ass your secret management. Think about what you're doing, but don't make it overly complicated, right? That was the goal of Whisper, right? Having a simple option, but that keeps things stateless. And so there are many options out there, but just find the one that strikes the right balance for your needs. Second thing is, while we can appreciate the simplicity of solutions like external secrets or Whisper and the power of modern technology like Kubernetes, we must beware of hidden state, right? It can creep up on you without you realizing it, and that's what happened to me. And the third one is do not fear statefulness. Okay. While stateless services are simpler to manage, you can design a system that can manage your state correctly if you need to. And so in conclusion, there are an infinite number of ways to manage secrets in production. And I hope this talk will help you find the design that works reliably for you. Thank you.